several times or several years, but it has a drop down during the last year or 2 years ago, and now it comes a little bit more into a situation that some of the developments will survive and will show a little bit more of effort and possibly of application. So, if I speak about that, I will start with the following. What are typical sources of energy? And if you speak about energy, then we can say energy is everywhere. Everybody has energy inside, and we can distinguish between natural and technical domains. If we are looking to energy in nature, then we can say we have the sun as the basis of energy, or we have wind and water, and some of the power plants are operating with the sun or with wind or with water. But also animals and plants have energy inside and they can work very well. On the other hand, it's hard to predict the appearance of a kind of energy if we are considering natural resources, especially if we are considering wind. Sometimes it blows, sometimes not. So it's difficult. If we are looking to artificial processes or technical processes, then we can see it's much easier to predict the appearance of energy, because each technical process is connected with losses, and these losses of energy can be harvested. So I come to a typical cause conversion effect chain, and we are considering the source of technical energy. And this could be a current flow, very simply. It could be a rotary motion, and it could be a move over by stepping or by driving. Furthermore, we have a reaction of that, and this could be a warming. It could be also a vibration or a compression on the material. And we have an effect, which is a temperature rise, a solid deformation, a dimension change, or a friction inside the material. So all of these effects can appear. And finally, we have the situation that we have a conversion. And the conversion is that what we can use as energy harvesters. So we can use thermoelectric effects, we can use solid state effects, and we also can use effects which basis on dimensional changes. So we have a typical conversion effect chain. Unfortunately, if we are considering technical processes, then we have to deal with the efficiency of a process. And the efficiency of a process is given by the input energy, or the energy which is given to the process, and the output energy, or the usable energy. And so we can define something like an eta, which is the typical efficiency of a process. In all cases of our technical processes, we have an eta which is below 1. And if we are considering that, then we can say, under these conditions, we have a situation that we have some wasted energy inside the technical system, and this energy, this wasted energy, is basic of engineering tasks, because engineers try to reduce the wasted energy. So, if we are considering energy harvesting in terms of technical processes, we have to deal with a situation that engineers, on the other hand, tries to reduce the source of the energy, which is the wasted energy. So I will come to the overview of my presentation over here. And so I will speak about some energy harvesting principles because I think not everybody is familiar with that. Then I will speak about a little bit the power adjustment which is required very often. We'll show you some industrial solutions which are available on the market. We'll say something about the energy harvested in sensor nodes, batteries as competitors, the big competitors of energy harvesters, and we'll show you some developments we have made in the past which are very interesting as far as they are going into the market possibly next year. Okay. As first to energy principles. The first principle I will show you is the magneto-electric conversion. If you are considering a magneto-electric conversion, then we have a device in mind, as you can see over here, which is shown over here, and you can see it here. You have a typical magnet system, you have two magnets. You can see the magnets, we have a pointer. The magnets are colored in black. Okay, thank you. The magnets are colored in black. And you can see here the magnets, and you have a coil, and the magnets inside as well, and you have a coil which is surrounded by that. And the coil is used to get inductive voltage. And this device here, as you can see, is a typical buoy, which is typically positioned in the sea, and the buoy moves up and down. And due to the mechanical construction, and we have here moving up and down, here you can see it in the other position. Due to that, we have a movement up and down, and this movement up and down leads to a certain kind of electricity. This is a typical device, as you can see it over here, and the demand of the device was about 1 to 10 watts, and the achieved was about 17 milliwatts, which is not very much. Another one is similar to that. Here you have an inertia system, and the inertia system, as you can see over here, is shown here. It's similar to that what I've shown you before. You have different cylinders, and inside the cylinders there are some magnets and some copper coils. And having these coils, and you make an oscillation of the cylinders, then you can generate, depending on the frequency and the acceleration, a certain amount of energy. The energy over here is about 0.35 watt for a frequency of 6 hertz, and with a higher frequency, the power is decreasing. The average power density, can you see, is about 1.6 milliwatt per cubic centimeter up to 2.4 milliwatt per cubic centimeter. This is another typical magneto-electric conversion system, and if you are looking to that, then you can see it consists of the magnets again, and you have some lifting magnets and floating magnets, and all of them will be forced by acceleration, and the magnet in the middle, the floating magnet, will move up and down, and in the diamagnetic plate there is a coil introduced, and this coil can get voltage, or a voltage will be induced. If you apply a mechanical input power of about 180 microwatts, you will get an output power of about 3.6 microwatt, which is an efficiency of about 2%, not more. This is another type of magneto-electric conversion, and here you have a typical box, as you can see it over here. And in the box there is a magnet of neodymium iron boron and a coil on top, and by moving up and down the magnet inside the box, you can generate current or a voltage inside the coils, and this leads to a certain kind of energy density, which is in a range of 0.7 microwatt per cubic centimeter. This is for divers, and divers are using such a small device, and they have inside a water turbine, and this is a typical turbine which is comparable with a bike generator, and the turbine is used for diving, so you have a pressure difference, and the pressure difference in the air, in the compressed air, delivers something like a flow of the air, and it goes through the water turbine, and it delivers a certain amount of energy, and you can see it over here for a diving of about 70 meters in depth. You will generate an energy of about 0.9 watt seconds, which is different to all the other things I have shown you. This principle is a magneto-electric conversion as well, but it shows more what people have invented to make piezoelectric conversion, and this is a mechanical construction to enlarge